Oh, beautiful. What's going on, everyone? Welcome back to another episode of Crypto Catch Up with me, Benny. Now, it's about 34 degrees here, Celsius in Brisbane today, and it's hot. Like, it's really hot. I went to go get a coffee, had a lunch, and I'm sweating. But it's been a month since I've done a video for you all. So I figured, hell, let's get on, let's get one done, let's get back into the grind and get education in the cryptosphere back on track. So today we're going to be going through attack vectors in distributed ledgers. Now, I'm talking about permissionless ledgers, Bitcoin, Ethereum, not your private counterparts or anything else like that. Now, it's not all of the attack vectors. It's not all of the software exploits. It's not all of the network topology attacks that one could do. It's just some of them to give you a little taste tester that you might then go and go, well, hey, I'm interested. I'm going to do some more research myself because that's what it's all about. Don't listen to me. Take little bits from everyone, formulate your own opinion, and come back with the good stuff. So let's get into it. Alright, so what is on the agenda? Well, we have, first of all, denial of service attacks, double spend attacks, and there's 4 of them we'll go through, Sybil Attacks, and finally, Eclipse Attacks. So let's not waste any time, and let's get right into denial of service attacks. So, denial of service attacks is something that is very common in a range of networks. So you've seen it recently with GitHub. They were attacked by 1.4 terabits of internet traffic, which try to bring down the servers which run their website. The attackers that is, were unsuccessful. GitHub absolutely handled it like a boss. They scaled accordingly, and essentially it was a waste of money and time for those attackers. So well done to the team at GitHub. But in terms of a blockchain, what does that mean? Well, it's essentially you're trying as an attacker to take down the network permanently or temporarily so it can't operate as intended. So what that would mean from a blockchain perspective is to flood the network with transactions, to flood them with millions of transactions that the network simply can't process. So Bitcoin only does 7 transactions a second. If you then give it an unconfirmed transaction mempool of millions and millions of transactions, it's going to be really hard for it to get through that, slowing the network down to a crawl where the important transactions can no longer get through. Now, Bitcoin has a service called replace by fee, but other networks don't. So you can't just pay more for a transaction to get it to the front of the queue. Of course, we could also spam it with large transactions, so ones with large amounts of data. Every node has to then process those, and then we get issues, which we'll talk about in a moment. So what's an example of this? Well, an example was Bitcoin. Back in 2015, it had a denial of service attack, or a DDoS attack, that ran for many, many months. Now, it actually forced transactions to, take around 20 seconds per transaction to be, I guess, confirmed or to be accepted by the mempool. You also then pushed, on average, transactions that were legitimate transactions from being processed within 0.33 of an hour to all the way up to 2.67 hours on average. So not obviously an individual transaction, but on average as a grouping. That's a long time. That doesn't suit me buying the coffee that I just got from Cafe 63. That would be really bad for business. So you can see where a denial of service attack has its merits from an attacker's point of view. So what can we do, and what does that mean? Well, it means longer sync times. Sync times for the nodes, because they have to download all the transactions, full nodes this is, not light clients like SPV wallets. They've got to sync the whole blockchain. They've got to store it all. It actually can force then nodes offline. So that's what we talked about with these large data sets, is that if a node that's running on a Raspberry Pi or something like that can't handle the actual computational power to actually run that large data set, or to perform a smart contract like it is on Ethereum, or has the HDD storage for that, or the hard disk drive space, they're going to drop off the network, lowering the obviously decentralization, and we have a flow-on effect. So what can we do against that? Well, we can charge higher fees. By charging fees, you stop them being able to spam the network with, inundated amounts of traffic because they have to pay for it. So it gets to the point where we actually want to have this economic disincentive that it would be more expensive to spam the network than it is to obviously make it worthwhile for them to attack. Now, that comes as a balancing act because obviously you charge people too much for an individual transaction, they're not going to want to do it. But you charge people less, then they might be incentivized to do a DOS attack. So obviously, part of the fun and games of game theory and mechanism design within Bitcoin and other networks. What about double spends? Well, we're going to go through a couple of them here. 4 of them. First of all, Finney attack. Came out in 2011 from Hal Finney, one of the original cypherpunks. It essentially talks about where I, as an attacker, would be mining a particular block, just like anyone else in the network. We're trying to get that reward. I've actually mined the block successfully. I hold off actually telling the network that I've done so. I do a transaction to a merchant that I know is going to respond straight away. So that might be to spend money or to buy something. We then reveal our block. That block then invalidates the merchant's transaction, but the merchant's already sent it back to you because they weren't waiting for confirmations like suggested. So the 6 confirmations in Bitcoin or 30 in Ethereum, which is around about an hour in Bitcoin for that, semi-finality. Therefore, we've got the money off the merchant or whatever it is that we did, and we also have successfully mined that block. Tops, great work to you. Then we have the race attack. Same concept again there, where I, as an attacker, send it the same digital asset, which I didn't even talk about what a double spend is. So let's reverse a bit. A double spend is you trying to spend the same digital asset twice. Something that's not possible in a centralized system like a ATM, because your bank knows that you only have $50 in there. You can't put 2 FPOS cards in and pull out $100. Now, back to the race attack. So the race attack is, I as an attacker am going to send the same, $50 worth of Bitcoin to a merchant and then the other to my personal wallet. And what I actually do though is that I force that personal network transaction to be, pushed out to the network faster. I want to expose it to a larger amount of nodes, therefore increasing my chances of that being confirmed by the network on a greater share than what the merchant's one is. Once again, we've gone to a merchant that's going to give us something back with, fast returns, not a lot of confirmations to allow this attack to take place. Moving on, the withhold attack. Now, the withhold attack is very similar to the Finney and the race, and it takes something from each of them, but it's a lot more computationally expensive and resource intensive to be able to perform. Essentially, you are, as an attacker, maintaining a whole chain or mining a whole chain of transactions by yourself. Now, while that's occurring, you're doing double spend attacks to merchants, getting the return. What then happens though is if you get to a point in time where you, as in Nakamoto consensus or in Bitcoin's consensus algorithm proof of work, have more computational power or a longer chain with more computational power than that of the actual network, you then reveal that to the network, and it obviously invalidates other transactions. Your chain becomes the chosen one. Once again, you've been able to perform some double spend attacks, but very, very expensive. Whew! 51% attack, or the Byzantine general's problem. This one is very well known. It's one of the one of the biggest things other than double spends that Bitcoin has been very successful at. So it has enabled the ability to ensure that the generals can't come together, collude, and take over the network. And the 51% attack is all about majority hashing power when it comes to Bitcoin. If you have 51% or more of the hashing power of the network, it enables you essentially to go back in time, rewrite blocks and transactions. But the caveat to that is, of course, you then have to beat the network to forging the next blocks. If you aren't successful in that, you are wasting your time and money. And people go, well, why don't, governments forge a 51% attack on Bitcoin, etc.? And you're like, well, they would spend $1 billion forging it for the short amount of time. And if they weren't successful in the brute force game, the puzzle that they have to solve for that nonce, they've wasted their time and effort. It's actually better for them to participate in the network as an honest node or an honest actor and get the Bitcoin reward of the 12.5. Sybil attacks. Now, Sybil attacks are very interesting attacks. It's actually a network attack. So essentially, you're trying to take over the whole network by pretending to be bigger than you are. So it's also known as pseudo-proofing, which came out of the cypherpunk movement. But Sybil came out of a book, and this catphrase caught on better than pseudo-proofing. So that's cool. And it all comes down to how cheap it is to create a new identity on a network. Now, when I talk about a new identity, a new node, a new stake, essentially in a Sybil attack, the network is normally unaware that it is occurring, and it can't detect it one is coming up or anything like that. So the value in this for an attacker is the higher number of nodes that they can achieve, the better it is for them. So like I said before, it would mean that, let's say in a group of nodes, you have a malicious actor, one node, that then can multiply itself in a range of ways, whether that be via IP addresses off the single node, a few other things there, which allows it to act bigger than it is. So if it enables them to pretend like it has hundreds of nodes on the network, it then can start to perform particular actions. And this is where the incentive is to perform a Sybil attack. So what does that mean? Where's the issues? Well, you can block transactions. So if you are having a nodes all around the network, and I, as an honest actor, am trying to send, $50 to mum, but this Sybil node is in the middle as a bad actor and goes, oh no, I don't want him to spend that money. They can block me from doing that transaction because they own a lot of bad nodes around the place, which are controlling the rules of the network through that node software. So that's obviously a downside. The second portion of that is around private transaction routing. So it takes a particular route, it uses particular cryptographic primitives. However, if you know where it starts and finishes, you know what the hell it was going on, and then you can start using metadata and other information to work out, who is this person, enterprise or otherwise. So just like in Tor browsers where they do 3 or 4 hops to a destination, and the hops only know what came, what is the next one. It doesn't know what is 2 ahead. So therefore there is no collusion between those two, destinations as it goes through the internet on its way to whatever server it may be. It's the same thing here. Is that if I am the honest node at the start, then it goes to a Sybil node, then it goes to a good node, then it goes to another Sybil node, which is the final destination, you have this kind of really good picture of where it started and finished. Now, it might not be perfect, but it starts inferring information which you could use in a malicious way. So how does methods such as Bitcoin and otherwise get around this? Well, proof of work is an interesting system. It doesn't care how many nodes you have. Nodes mean nothing in a proof of work system. It's down to raw hashing power. And because of that, if I had one node which 100% of power and I broke it down into 9 other nodes and had a total of 10, it actually wouldn't give me 100% of hashing power across all of them. I would have to break up my hashing power to be 1/10 of that across each node. That doesn't suit me in a Bitcoin system because that hashing power, that total hashing power, is what I need to try and win a block reward. So what's the point? Once again, getting back to that incentive, disincentive. Proof of stake. Proof of stake. You have to have a stake up. Now, once again, if you have a node that broke apart and the rules of the system are that you have to put 32 ETH up to have a stake, well, breaking up the stake's not going to help you. You're going to need to have another 32 ETH. Once again, we talk about how cheap is it to create a new identity on that network. It's not, and therefore it obviously lowers the risk of a Sybil attack occurring. Finally, Eclipse attacks. Now, Eclipse attacks are similar to that of a Sybil attack, but Eclipse are only done on particular users or a user. Now, that user might be a merchant or a merchants, that McDonald's or something like that. It's all about isolating that particular node or merchant from the network state, so you actually control the transactions they're incoming and outgoing from them. Not outgoing, sorry, but what they're actually accepting in. So they'll send transactions out, you then return something to them, happy days. What it means though is that they no longer know what the real version of truth is in the network. You're controlling that. You can feed them propaganda. And so the issues with this is that it allows people to split mining for a potential 51% attack. So if there's a really strong node, like a lot of hashing power, you can try and control that node through an Eclipse attack. And what they actually do is Bitcoin has 8 outgoing connections, Ethereum 13, and they try and actually control all of those outgoing connections for where transactions are going and things like that. And by controlling that whole node, essentially you take that hashing power away from the network. They think they're doing the right thing and playing by the rules, but essentially only this hashing power is left over, which might give you the ability to perform a 51% attack. The issue there is also zero confirmation double spends could occur. Once again, you take a merchant away from the network, you hit them with a merchant attack or an Eclipse attack on that node. You could do a double spend. They wouldn't know any otherwise because you've actually propagated that transaction out to the real network. They've accepted it. Once they join back again, they realize that they've got burnt by you. Well done. So how do we stop things like this? Well, random node selection. By randomly selecting nodes all the time, you're not always going to get, that malicious actor potentially that is within your small world network, which is what Bitcoin is. It only takes one hop to get anywhere within the Bitcoin network. Node information storage is important. So Ethereum and things like that, when you're using bootstrap nodes to connect to the network for the first time, which I believe in Ethereum there's only 4 or 5 of them in the world. You then find out who's around you. You push out transaction and go, hey, who's around me? I want to know the nodes around me. So you want to store that information. So next time somebody joins or leaves the network, or you join or leave the network, you know who's kind of been a good actor around you in the past. Are they still good? We'll soon find out, but it allows you to control that a little bit better. And finally, increasing the number of the connections. So 8 and 13, like I talked about earlier. The 8 and 13, what that means is if we increase that, it's a lot harder for somebody, an attacker like myself, to perform an Eclipse attack, because I actually have to do trial and error to work out where your connections are going to and then to control them. So the more of those there are, obviously, economies of scale makes it a lot harder for me. Like I said, guys, that is just some of the attack vectors that are happening fairly frequently in some networks, especially forked coins. Bitcoin Gold got smashed with double spend attacks, 51% attacks and things like that this year. There's a lot of other issues that are out there, but obviously this is just a subset of them. I'd love to know, what is your favorite attack, or something maybe you'd like to look forward to or learn a little bit more about? Post it in the comments below. As always, if you can share, like, and subscribe, I'll hopefully get another video out for you shortly. Thank you all. Enjoy the rest of your weekend.